Okay, welcome everybody, and welcome to CERN, and thank you for coming to visit us today. It's really a pleasure to welcome you here. My name is Pauline Gagnon. I'm a physicist on ATLAS experiment, and I'm also a communicator with the CERN communication group. So today I'll go and attempt to tell you what does a Higgs boson eat during the winter and other essential facts. So I'll just give a minute to those people here to sit down, and we'll start right away. So there's lots of room at the back, at the second level here, so it's easy to reach there. So what I want to do first is tell you a few words about the lab here. CERN is the European Laboratory for Particle Physics. It has about 12,000 scientists coming from 99 different nationalities. In fact, we have 63 different countries participating into the lab. It's financed by European countries, but many other countries participate, such as Canada, the country I'm from. The common goal for everybody here is to find what matter is made of. So that's what we are doing. And if we were at Legoland, so this is a picture of the Copenhagen harbor, as seen as you can find it in the Legoland, where everything is made of Lego blocks. And if I was to ask you there, what are the smallest particles, the smallest grains of matter, it's very easy. All I would have to do is take one of those pieces, shatter it, and I would see the smallest pieces coming out, and then we would know what matter are made of, what are the fundamental particles. But in the real matter, when we look here, it's a bit more complex. So if I take any type of matter that we see around us here, we know that from high school, we know that this is made of atoms. And inside the atoms, you have the electron orbiting around the nucleus. Inside the nucleus, we have the protons and the neutrons. But inside the neutrons and protons, that's where we find the quarks. If I ask you now, which ones are the fundamental particles, in this picture, we only have the electron and the quarks. Those are basic ones that you cannot break apart. So those are fundamental building blocks of matter. In fact, with those quarks, I can take up quarks. I can take two of them. Up quarks have a charge of a 2/3, an electric charge, 2/3 of the charge of an electron. And down quarks have the charge of -1/3. And I can combine them. Will this work? Yes. I can take two up quark and one down quark, and if you add up 2/3 with 2/3 plus 1/3, then I get +1, the charge of the proton. Likewise, if I want to build a neutron, all I need to do is to take one up quark and two down quarks, and their electric charge adds up to 0, and that's your neutron. So with that, I can take neutrons and protons, build all the nuclei that we have, all the different nuclei for atoms, and you can build the whole periodic elements. So the building blocks of matter are electrons and quarks, and with that we can make any chemical element. We have now a theory in particle physics to describe the world, which we call the Standard Model. The Standard Model tells us two things. It says that all matter is made of elementary particles, fundamental particles. And the second thing is that these particles interact by exchanging other particles. And the way it goes is that, imagine that you have two skaters on a very perfect piece of ice. And then they evolve together, and one throws a heavy ball to the other. So both of them will recoil from this action. So now they have exchanged a particle, a huge snowball, and that makes them deviate. So there was an interaction between them. That's how we describe things happening at the fundamental particles level. And the Standard Model now tells us that matter is made of fundamental particles that you all see here. And these are the nice fluffy ones that are locked in my office right now. I couldn't find my key this morning. But it's made by the Particle Zoo. You can buy those particles. So we have all of them. We have leptons, the first family, and quarks. Leptons, you all know the electron. But there are also muons and tau, which are all very similar to electrons, but much heavier. And they all come with their own neutrino. Then we have another family of quarks, And those are up and down, I just introduced them, but there's also the charm and strange quarks, which are a bit heavier, and the top and bottom, which are much heavier. The top quark, in fact, is the heaviest particle we have ever found. Those particles, it's a bit strange because to make all ordinary matter, you only need what we call now the first generation, this first row here. The other ones, we can make them appear in our accelerators here, or they even appear in cosmic rays, but you don't, normally they're unstable and we don't find them. So that's the first part. All matter is made of fundamental particles. The second part is that they exchange particles that we call bosons. We're getting closer to the Higgs boson. So boson is just a type of particle that is associated to a force, and particles exchange them and that's the way they feel those forces. For example, the strong interaction is what you find inside the protons. Quarks are bound together by gluons, and it comes obviously from the word glue that glues them together. Then you have the electromagnetism that is mediated by photons. The weak interaction, that's the force that is responsible for radioactivity. And then there you have three bosons, two Ws, one with a positive, the other one with a negative charge, and then the Z boson. We think that with the gravitation, there is another particle associated with it, graviton, but we have never found it yet. We haven't found it. And finally, the Higgs boson, which we just found last July. So that's the model that we have to explain what matter is made of. But we have a major problem with this model. It seems to work really well to describe everything, except that when you put equations to describe those forces, the equations were not really describing the reality. What we had wrong button. So the standard model predicted massless particles. So with all the equations, it was only massless particles coming out, whereas we knew that, in fact, the W and the Z are massive particles, whereas the photon, it's true, this one is massless. So we needed a way to fix the equations of the standard model to generate massive particles. That's where many, many theories came into play. And in 1964, building up on the work of many others, there came two Belgian physicists, François Engler and Robert Brou, and both of them published a first paper on something that is now called the Brout-Englert Higgs mechanism. So they were the first one to publish on that. Peter Higgs published a month later, and he specified in his paper that there was a boson attached to it. And then finally, there were three more physicists, Kibble, Guralnik, and Hagen, who added more information. But all these people contributed essential pieces to this theory. So if there's going to be a Nobel Prize for it, it's really complex because nobody knows exactly who should get it. And maximum 3 people can have it. So to generate mass, we need 3 things. So we had this problem in the standard model. We have a nice theory, it works well, but there was no way to generate the mass. So what do we need? We need 3 essential elements. The first one is the Brout-Englert Higgs mechanism, which is just a mathematical description. It's just a mathematical trick, and I'll describe that in a second. But this trick describes, in fact, a reality, a real physical entity which corresponds to this mechanism, which we call the Higgs field, which is very similar to the gravitational field, if you wish. And then finally, the Higgs boson is just the materialization of all that. So it's the proof. When we found the Higgs boson, we were proving, in fact, that this field existed. Okay, I'll go now over all those points to make it clear. So the Brout-Englert Higgs mechanism. As I told you a minute ago, the theory predicted that we had 4 massless particles. In the equations, that's all we could get out of it. But those 4 sad-looking bosons did not correspond to the reality. So the great idea that Brout-Englert and Higgs had was to, in fact, add 3 fictitious particles. Those are called goldstone bosons. And what they do, they take the 4 massless bosons, the 3 fictitious particles, they put all that back on the board, they shake the equations, and poof, comes out the four particles, the four real ones. And I tell you, this is about this. When I was in a graduate school, we had the exercise of taking the equations, mixing them all out, and at the end, you see those four particles coming out exactly as they are. And it's not very complex. It's a fairly easy exercise that we can do within a page, which is rare in physics. So it really works well. We get our four bosons, the photon, which remains massless, no electric charge, two W's, one with a positive, the other one negative charge, and the Z boson. Those are exactly the particles that we find in our accelerators. So it's really nice. It really works. But to say that it looked brilliant mathematically, but we needed the proof that it was true. So to go a bit further, I need to introduce three concepts that we use in physics. The first one is the concept of mass. When we talk about mass in physics, in fact, we're talking about the resistance to movement, resistance to motion, so resistance to a change in movement, in fact. So I put here the example of a boat, a massive boat. And this boat is very massive because it has a lot of resistance to motion. If you try to get it into motion, it's very difficult. You need a lot of energy. And likewise, to stop it, you will need just as much. So that's the first thing. In physics, mass is resistance to movement. The second one is the equivalence between energy and mass. Energy and mass are just two forms of the same essence. Just like water and ice are the same, it's the same essence, but in two different forms. So the energy in this equation, the E, represents the energy, the M represents the mass, and C squared is just the square of the speed of light, and it's the exchange rate. I'll give you another example. For example, if we say that money is some essence, something, and I can have it in different forms, like in my pockets right now, I have Swiss francs and euros. So, and between the two, there is an exchange rate. So you could say that energy and mass are just equivalent, but you can exchange one for the other. The third concept that I want to introduce is energy conservation. Energy can take different form, but the total sum is never lost. So if you start with a certain amount of energy, just picture, for example, a glass filled with a liquid, and that's your amount of initial energy. Well, this energy can be in different form. It can be in the container called movement, or it can be associated with the mass. So an elementary, a fundamental particle will have part of its energy in the form of its mass. From the equation E equals mc squared, it's equivalent. So let's get to the Higgs field now. Imagine that you're running on a beach. You're running in the air. I'm going to give you a simpler example, and then we'll go to the real thing. But just to build up a bit. So imagine that you're running on the beach, you're light and free like air, and there is nothing to stop you. You feel so light. But then, whoops, you have to run in water. And all of a sudden, there is really a drag force on you, and you start feeling massive. You have acquired resistance to motion. So the Higgs field is a bit like that. It makes the whole space sluggish. Every particle that goes through it makes, every particle that goes through it starts interacting with the field and then cannot go straight. And it slows it down. So this is an image just to explain it, but something that is a bit more accurate in physics. Physicists were a bit picky about how we define things. So let's imagine now how it works. So imagine that you have empty space without a Higgs field. So the particle can go from point A to B at the speed of light. Okay? I'll do that a bit slower now. So the particle can go from A to B on a straight line. There is no Higgs field. All its energy is in the form of movement. It has absolutely no mass, and it travels at the speed of light. Now, let's turn on the Higgs field. So we turn on the Higgs field, so the field appears, just like I would turn on the gravitational field, if I could do that. And then my particle wants to go from point A to point B, but trying to do that starts to get encumbered in the field, and it goes from point A to B much slower than before. So if I look at its energy balance now, it has less speed, therefore there is less kinetic energy, less energy associated with its movement, and so the difference has appeared in the form of mass. So that's really what happens with the Higgs field. Now, how did this Higgs field appear? You can look at it as a property of space. Like space has dimension and all that, but one property of space is to have the Higgs field. As soon as the Big Bang was over, this field appeared. That's just the way it is, just like time appeared. You know, nobody questioned what is time. It's a property of space around us. So, the important difference between the runner in water and this case is that the Higgs field gives mass without dissipating energy. Because when there is a friction, dragging force, you lose energy, whereas here you don't lose energy. So that's the important point, important difference. How much mass will a particle get by interacting with the Higgs field? In fact, it only depends on how strongly it interacts with the field. So on the vertical axis here, I show the Higgs coupling, which is just a way to say how much it interacts with the field. And here it's the mass of standard model particles given in units of energy, GeV. So you see, for example, a particle like the tau lepton. It's fairly light. It interacts very little with the Higgs field, and therefore it's fairly light. So both are logarithmic scales here. The B quark is much heavier, and this one, it happens because, the bottom quark interacts more, the coupling is higher, and therefore it has more mass. And at the top here, the top quark, the heaviest one, is the one that interacts the most with the field. So the more you interact with the field, or the more you get your feet entangled in that field, the less you can move, and therefore more mass you acquire. And the photon is really special because this one will remain massless, because it does not interact with the field, and that's the only particle that can keep going at the speed of light. So the photon is massless, and it goes at the speed of light. Whoop. So we always explain that the Higgs boson is really important because this is what gives matter its mass. But that's not exactly correct. And in fact, if we look at it, look at the quark masses. If I add up the mass of the 3 quarks that we find inside the proton, we have 11 MeV for the sum of the masses of the up, and down quark, whereas the mass of the proton is 938 MeV. So you see that about 99% of the proton mass comes from the binding energy. So look at the gluons here, keeping everything together, those little springs in white that you cannot see there. So those are the binding energy to keep all that. This is what is giving mass. Remember, energy and mass are the same, just two different forms. So most of the mass of the proton comes from the binding energy. So now you could get a bit annoyed with us saying, so why did you make such a fuss about the Higgs boson? Because without the Higgs boson, all particles would have remained massless, like the photon, and zoop, going at the speed of light. And if that was the case, you could not form bound state. You could not form protons, neutrons, nuclei. You would not have any matter. If the fundamental particles inside the atoms and the nucleus were massless, then you couldn't form a solid state. So this is why the Higgs boson is so essential. It gives the little mass that is needed to slow them down enough to be able to form a bound state. Okay, so let me summarize now the 3 aspects. There was first a mathematical tool that the Brout-Englert Higgs mechanism is what gives masses to the Z and W, for example, but without affecting the photons. So this is just a trick of reshaking the equations. The second aspect is the physical entity, the Higgs field that filled the space shortly after the Big Bang. And that's really what every particle interacts with. And finally, I haven't said a word yet about that darned Higgs boson. So it's an excitation of the field. So let's look at this. Imagine that the Higgs field is just like the surface of the ocean. So you have the surface nice and quiet, but you know, a wave is just an excitation of the surface of the ocean. So imagine that there is, for example, an earthquake. Then it can create a tsunami, so you have this devastating wave going. Or you can get the energy from the wind or from the gravitational pull of the moon. So waves are just excitations of the surface of the ocean. And our little Higgs boson is simply an excitation of the Higgs field. So what we do, how do we get the Higgs field excited? And that is what the accelerator here is all about. So what we do, we need to concentrate a huge amount of energy in a small point in space, and that's the role of the Large Hadron Collider. In doing that, you can get the Higgs field to the next excited state, just like you can excite an atom hydrogen, for example, by exciting the electrons. So the Large Hadron Collider is this huge tunnel that we have here. It passes just across the street underneath the experiment Atlas. And we have 27 kilometers with the protons going at nearly the speed of light in both directions. And then they smack, the operators bring the two beams into collisions right at the center of our detectors. Our detectors are built around those points such that all the energy that is put there materializes in the form of particles, and then we see new particles coming out of there. So the energy materializes, and those big detectors are just like giant cameras, and we take snapshots of all the debris of those particles. Because what happens with a Higgs boson is that it's a very unstable particle. So as soon as you create it, it's going to break apart. And to explain to you what is the decay of a particle, what does it mean that the Higgs boson decays? It means that imagine that it's a coin, €2 coin, and then you could break it apart into two €1 coin, and those can also be broken apart into 50 centimes. So this is the type of the decay that you can find. So the €2 would represent the Higgs boson, and it goes into 2 Z boson, and a Z boson can go into 2 muons. But this is not the only way to get 4 pieces of 50 centimes. You can also get that if you start with €2, 2 single pieces of €1. And then, again, it could be that we start finding at the end in our detector, we could find 4 muons, but the whole question is to find out, when you have this beautiful event here from Atlas, you see in red, those lines in red are muons, so those heavy types of electrons. And you have 4 of them, and the question is, does it come from the decay of a Higgs boson into 2 Z bosons, or was it simply 2 Z boson? And what we have to do, I'll come back to my example of coins. If we started with €2, if we break it apart, the 4 coins that we get at the end, it will always add up to €2. But if I take randomly what I have in my pockets, here I have it's in francs, but it's 170 or something like that. So if it comes from 2 separate particles, the value that it gives is something random. And if I put it on a horizontal axis, the values that I find here are the 4 muons. And if I see it on the horizontal axis here, what you see is the mass of the combined 4 muons. And the red histogram here is just the number of events that I would expect to find from 2 Z bosons. So they would give me random values, but we can evaluate how many we would expect. And in the black dots are the real points that we found. So in a second, the animation will restart. We're just showing here that, in fact, there was a small excess, and this corresponded to the Higgs signal. So this will play again in a second. So here we go. So you can see at the top the dates. So we can see the events as they came up. And if there was only events coming from 2 Z bosons, the dark dots should mimic the red distribution. But you see that right here, we start seeing way more events than we're supposed to come just by the 2 Z bosons. So in fact, this excess, now we will zoom in that region, And you see that the excess corresponds exactly to what we would expect if there was a Higgs boson. So this is how we could find that there was a Higgs boson. We did that in 3 different decay modes, which was 3 different ways of giving the change, and then we could tell that we had found it. So have we found everything? Are we happy with what we have here? No, sorry. The problem we have is that everything that we have now, this beautiful standard model that explains everything, only explains 5% of the content of the universe. So, we haven't done so well. Astrophysicists, when they look at the universe, they can see that there is a strange type of matter, which we call now dark matter, which has nothing to do with the matter that we know, quarks and leptons, has nothing to do with the type of matter that we are made of, and it's not either antimatter. Antimatter is just like matter, in fact. So when we look in the universe, they see that all the stars, all the galaxies, pulsars, quasars, you name it, all those things account for 5% of what is out there. The rest is dark matter and mostly dark energy. And dark energy is even weirder because we know that since the Big Bang, the universe is expanding. But not only that, just a few years ago, 3 physicists found out that it was, in fact, the expansion is accelerating. And if you're driving your car and you want to accelerate, you need to give energy to your car to accelerate. So there is some energy that makes the acceleration, this expansion accelerates. And we don't know at all what it is. So dark energy, we're really in the dark, and it has this name. So what we know so far is only the tip of the iceberg. Most of it is absolutely unknown. So if you're a young person studying physics, go for it. We have a lot of work ahead of us. Thank you very much for coming. I think I have 4 minutes before they start broadcasting from the globe, the next lecture. I can take a few questions if you have easy ones that I can answer in 4 minutes. And you can press the button in front of you. There are microphones in front of you. We're in the... Someone... Okay. Yeah. It's good. Just speak in it. No, go close. That's it.
What's the difference between dark matter and dark energy? Isn't it the same form?
No. Dark energy is what we associate with the expansion of the universe, whereas dark matter is something else. And we can feel these effects of the dark matter inside galaxies, rotating galaxies. We can see that there is way more matter inside the galaxies than what we see from the light, which is visible matter. But this extra dark matter is what binds the galaxy together, that creates the gravitational field that is necessary. Otherwise, everything would be scattering. So they're spinning too fast. Normally, everything should be scattering. But no, we see that they're holding. So there is more matter than what is seen. So there is a difference between the two. Good point. Yes, please. Press your button. Yeah, the big button. Yeah, that's it. Well, I was, it was announced on the eve of you're asking me how I felt before the discovery of the Higgs, or when it was announced? Yeah, it was neat. It was really neat. And it was announced here on the 4th of July, just on the eve of a major conference where we expected that the new results would be shown. And that conference was in Melbourne. So I had been traveling, and it was all jet lag and all that. And then the last plots were sent to the Atlas collaboration. So there I could see, they have it, we have it. And the only place where I could connect was in a McDonald's where there was free internet. So I was there, and I couldn't talk to anybody there but hamburgers. But it was really exciting. But no, it was only us, Atlas, that I had seen. I had not seen the results from the other experiments, CMS. The reason we have 2 experiments like this is because we want to cross-check each other. We work with very different technologies. The detectors are really built differently. So if we see something and both say we see it, then it's a real thing. So then when I went to the conference the next day, and then I saw that they also had it, Then it was, woohoo! It was really nice because physicists are usually tame. I'm not standard, but physicists are usually tame, and there in the room, people were really going, and so that was fun. I had never seen that. That was pleasant. Because, we've been working on this as experimentalists at least 20 years, but it had been predicted 48 years before. Yes, last question.
It's space quantable.
Space quantable. I'm not a theorist, I'm an experimentalist. So this is out of my realm. As far as I know, it's not, but I cannot answer. I cannot answer that. Quick one, yeah.
What do you know about the gravitons?
We know nothing about the gravitons. We just don't understand why this force, gravitational force, why is it so weak compared to the others? If you compare the gravitational force with the electromagnetic force, it's 10 to the minus 40, the strength of the other. So it means that it's 0.00040 zeros 1 times the strength of the electromagnetism. So it's the graviton. Every force comes with a particle that mediates it, and if we don't see it, it's weird. We don't understand that. Gravitation is the least understood of the forces. But some people think that it could be that its strength is being lost in hidden dimensions that we would not see. So that's exciting. Don't stop reading science fiction. Just go for physics. It's way more exciting, I tell you. We just have mind-blowing stuff. For respect for the next speaker, I will have to stop here so they can start broadcasting the next. But thank you very much for coming.